The title of this slide is Bridges, by the way. I use the word switches. They are the same in some sense and not in other sense. And this is an annoying feature of this field, that the terminology is a bit used in sometimes inconsistent ways. I try to bring some consistency in the framework of this course, which is an academic framework. When you go to real life, you will have to use the ambiguous terminology. For me, a bridge is an architecture name, is the name of a function. It means an intermediate system of the MAC layer. In other words, it's a system like this one that receives Ethernet packets, analyzes their headers, essentially their MAC destination addresses, and does something with them, sends them forward to another destination. Intermediate system of MAC layer. Of MAC layer means it looks only at the header of the MAC header. A switch is a product name that means typically a bridge implemented in hardware in a small box that you can buy for very few francs. So switch is a product name as opposed to bridge, which is a function name. Now you can find functions in very different ways. You can have a bridge embedded in an ADSL modem, for example, in which case you call the box an ADSL modem even if it has a bridging function. Right? And invariably we give the name of the function to the box as well. This is where the confusion comes from. We call this machine a web server, even though the web server is only a program inside the machines. The machine is a PC, a Dell PC or a Linux box of some kind. So this is where confusion might come from, but we'll have to live with it. It helps if in your head somewhere you make the difference between architecture and the implementation of a given architecture product. So a switch is always a bridge. It's a dedicated box that does essentially bridging. A bridge, as I illustrated, is a queuing system. So inside the bridge, there is no CSMA. There's only queues, right? So there's a processor that does the scheduling and the arbitration. So there's no need for a distributed protocol. Very complex bridges might have a distributed protocol, like any computer has a distributed protocol for accessing the bus of the computer. But this is invisible to us. That's internal stuff of the machine. In particular, one way to phrase it is that a bridge separates collision domains. So I'm showing here a network with hubs. So hubs are like cabling systems. So it's the same as if there would be nothing. And the bridge here connects those three areas that are now three collision domains, which means in particular here that it is possible for A to send a packet to the bridge, and for C to send a packet to D, and for F to send a packet to the bridge. Those three things can happen exactly at the same time. What is not possible is that D sends a packet to C, and at the same time C sends a packet to the bridge. This is not possible. This is one collision domain. There is one instance of the CSMA CD protocol in this pink cloud here. That's important to understand. How does a bridge know to which port it should send a given packet? For example, how does it know when it has a packet to send to E that it should send it on its port number 3? Well, it has to have a table. If a bridge would be a router, we would call this the routing table. Now, people avoid to call it the routing table, though formally it's exactly the same thing. How do you configure the routing table? As you have started to see, and you will painfully discover through the rest of the labs, routers need to be configured. We need to have routing information, otherwise they don't work. Now, if you buy a bridge or a switch from Migros or MediaMarkt, you don't do anything with it. You just connect 3 devices and it works. So it's plug and play. Where's the magic? Well, the magic is here. A bridge listens to all traffic and observes the source MAC address. So it reads the destination, it listens to all traffic and learns from the source MAC address. So for example, when F sends some data to someone, to the bridge, then the bridge sees, oh, there is this MAC address F that's on port number 3, so it will put it in its table here. whenever someone has to send something to F, then it will send it to port number 3. So they spy and use that information. Now, of course, you need to bootstrap things. I mean, in order to listen to the source MAC address, you need that traffic happens. So if it must continue to work even if the bridge doesn't know what to do. So the key thing here is that if the bridge doesn't know, it sends it everywhere. It does a broadcast. We find again the broadcast that exists in local area network. The price for plug and play in local area networks is the use of broadcast. And of course, broadcasts are bad. You try to avoid them as much as possible, because if some hacker manages to gain control of the broadcast, you can kill the network. Plus, you might leak some information by sending the packet to everyone. But that's what bridges do. So if the destination address is not heard, for example, when the bridge sees for the first time a packet to F, and F has never spoken so far, then D is sending, for example, for the first time to F, then the bridge will send it on all ports, except, of course, the ports on which the packet arrived. So it will send it to ports 1 and 3. If F never responds, then the bridge will always broadcast. But it's extremely rare. One-way communication is extremely rare. It exists. It exists in some, for example, airports where you have the display TVs. You have 1,000 display TVs. You have one server that sends the displays. Since the display is refreshed every second, you don't need acknowledgement or whatever. You just continuously send data, and the displays that just show it. If the packet is lost or corrupted, you'll see a little blurb, and then the next packet arrives and corrects it. So there are a few protocols like this, but they are extremely rare. So the assumption is that for those rare cases, well, you will continue to broadcast, or you need to fix it in some other way. In general, if D speaks to F, F will send something to D. For example, if D uses TCP, F will send TCP acknowledgement. So there will be traffic back, and then the bridge will learn that F is on port 3, and that will close the loop. Consider this little network here, where X is a hub or a switch. A hub means here a concentrator, right? Layer 1 repeater. How many frames can be transmitted in parallel in each of the cases? Five more seconds. Okay, the majority vote that seems to be the second one is the correct one. If X is a hub, it's as if I had a big shared cable between everyone. Even though the cable has a weird shape, it's a tree, but it is a shared cable, so there can be at most one packet at a time. If it's a switch, there are 3 collision domains. Inside each collision domain, there can be 1 packet sent at a time. Therefore, there can be 3 packets in parallel happening in this network. Okay, that's not the end. Yes, question?
If you needed 6, because you can receive and send at the same time. If like per collision domain, you can send and receive. So you have actually 6 collision domains, each on one wire.
But here not, right? Here you have 3 systems on each. So even if you have a separate cable, it's 1 collision domain. So you could, in theory, but this is not exploited. If you truly have a hub here, you cannot send and receive at the same time, because that is a collision. Right? Well, that's an important thing. That, of course, we want to fix. And how we fix it is the next step of the evolution, exactly your observation. It is stupid to use Ethernet in that way. Even if you put switches, you still have some inefficiency. In terms of terminology, if we run Ethernet only between two machines, like for example between an Ethernet computer and a switch, if we use the native Ethernet, we have what is called a half-duplex link. Half-duplex means you have a cable or a channel on which duplex means it works in both directions, and half-duplex it means not at the same time. Now, if you use strictly the CSMA CD protocol, two ends cannot speak together. That causes a collision. Therefore, it's half-duplex. Right? So if you use the standard Ethernet between two machines, it's half-duplex. Right? Now, if you use twisted pair with separate wires for each direction of transmission, it is stupid. So you should not do that. You should allow transmission to occur in parallel if you know there are only two systems. This stupid idea, very simple, not stupid, but very simple, has a name. It's called full duplex Ethernet. Right? So this is what I call less is more. In fact, we started from something complicated, smart, CSMA CD, on shared medium cable, and at the end we remove all of that and we give it a name to say we have invented more. We do full duplex Ethernet, means essentially we use Ethernet only as a physical layer, point to point. That's all that is happening when we use full duplex Ethernet. Now you can use full duplex Ethernet only if there are two devices in this collision domain. So there must be a switch at the end. Right. So in the figures we saw with three systems in the same collision domain, that cannot work. Okay. Typically today, most devices, they sense whether by sending special physical layer signals, codes in fact, they sense whether they are connected to a hub or a switch. If they are connected to a hub, a physical layer repeating device, they will work in half-duplex Ethernet. If they are connected to a switch, they will work in full duplex Ethernet. So far, we've used only one switch in our configuration. Now, most networks are small, so in many cases that's sufficient, but in networks it's interesting to have more than one switch. So the method of learning the MAC addresses, which is essential for keeping the bridges plug and play, works if we extend to a network. For example, here, if I zoom on bridge B3, when a packet comes from X, for example, then it will arrive on port 1. So B1, assuming it has a correct table, will forward it on port 1. That will send it to B3, and B3 could have a table that says it's on port 1. In other words, B3 sees the network as if X was directly connected. Whether it goes through another bridge or not, it continues to work. At least it seems so. Does it really work? So try to simulate in your time, in your head, what would happen in a network like this one. Can you imagine that it works or not? I close in 5 seconds. And the correct answer is it works on this case, which is a special case. So, what is special about this case?
There's
No loop.
There is no loop, right? Are there usually loops in networks? Well, yes. If you build a network, you probably want some redundancy, just in case something breaks. If you have some redundancy, that means you have parallel paths, so you have automatically loops. If you follow the different parallel paths in a certain way, you will always create loops. So a network that has no loop cannot have redundancy. So most networks, except for the very, very simple ones, any network that is designed to work well in presence of the failure of a link or of a bridge will have some redundancy. Now, if there is some redundancy, like in this network, where the three bridges are connected to each other, there is a chicken and egg problem. The switch 3, for example, which is this one, doesn't know whether A, which is on the left here, is on port 1 or 2, because a packet from A assumes switch 1 doesn't know, so we'll broadcast it. A packet that has to go to some destination. So switch 2 will do the same thing, will broadcast it. Switch 3 will do the same, so the packet will be sent to all possible paths. So switch 3 will see packet coming from A, either directly from switch 1 or from switch 2. So it will not know, and it might oscillate, so there is a problem. So the method of learning, it's true, propagates to several switches, and it works well if there is no loop. That's easy to convince yourself, like in the previous example. But if there are loops, it doesn't work. How can we fix it? Well, the simplest way is to avoid loops. There might be a smarter thing. We could say we pick the direction that has the shortest number of hops, a bit like we will do in IP layer. But the solution of the MAC layer is the simplest. In general, if you try to guess and find the simplest, 95% of the cases you will find the correct solution. So what bridges do today, they force the active topology to be free of loops, which is a bit subtle. It doesn't mean we require that a bridge network has no loop. We want to have loops for survivability. We want that the network is able to survive destruction of some links or loss of some links or some bridges. However, the bridges will speak with each other, and they will through a smart distributed algorithm that's called the spanning tree protocol that we'll see at the end of the course. The spanning tree protocol will make sure in a fully distributed way that all the bridges agree on something that is shown here. What is shown here? Well, those bridges, switch 22, switch 44, and switch 9, have agreed to disable the ports that are marked with a red cross. Disable, that means the ports are physically operational, but somewhere the hardware has decided not to use them. Not to use them for forwarding traffic. But the bridges will continue to talk to each other just to monitor that things are okay. And if something changes in the topology, if, for example, if one link or one bridge is destroyed, they will perhaps reopen a port that was closed. So in other words, the bridges will deactivate some ports in order to make the active topology a tree, which will avoid the problem of those loops in the learning process, but has a drawback, of course. The forwarding topology will be a tree. So the loops in bridge network can be used only for increased reliability, but not for increased throughput. In the internet, there are loops, for example, between Switzerland and the US. There are many parallel paths, and they're all used together. So we increase throughput by having parallel paths. In a bridge network, even if we have parallel paths, for example, if there's traffic from switch 7 to switch 22, it will go via switch 1. It is only if switch 1 fails that this link will be open and traffic will go here. So we don't increase the traffic capacity from 7 to 22 by having an additional link. We don't increase capacity, but we increase reliability. This is how bridge networks work, whether you like it or not. And that's a consequence of all the requirements of the past. Right. How this is done completely automatically is a very beautiful algorithm that we'll describe at the end of the course, but right now we can skip it. All we need is to know that it exists. An important thing to remember is that in that story of evolution that I've concluded now, an essential requirement is that anything we do to the network should be transparent. We keep the PCs, the machine, running Ethernet the way they did before, and then when we change things in the network, that should be completely transparent. Also to the software. It's not transparent, of course, at some level. If I connect my PC to a hub or a switch, they will talk to each other and the PC knows it's a hub rather than a switch. So it's not transparent. However, anything, the MAC layer itself and the IP layer that uses the MAC layer will not see the difference. So from a protocol viewpoint, bridges are transparent to end systems, which means that if this one is talking to this one, it should be exactly the same as if they would be directly connected. You can connect two Ethernet devices directly with an Ethernet cable without any switch or hub, by the way. So if you connect them together, or if they go through a complex network of bridges or hubs, it should be exactly the same from the operational viewpoint. The Ethernet packets are exactly the same. There is no additional protocol required to make it work. Of course, there's a difference, otherwise we would not do it. There's a difference in performance and in ease of management. If you have switches, it's easier to manage than to have cables that go from all machines to all machines. And typically, a bridge, it has higher performance because, not that the bridge itself has higher performance, but a network with bridges has higher performance because now it has separated the collision domains. You have a bit network with 100 machines that is using hubs. The 100 can, only one out of 100 can talk at a time, whereas in a bridge network, with a powerful bridge in between, the 100 can speak together if the bridge has enough throughput to support the traffic of the 100 machines. So back to my question now. Now all the machines are switches. How many frames can be transmitted in parallel? Five more seconds. Larger than 6 is the correct answer. Because now each of the links can be a full duplex link. So between D and switch 2, there can be 2 frames in parallel. Between C and switch 2, the same, assuming the switches have enough buffer and enough processing power to do that. So in total, there can be on every link 2 frames. There are 9 links. There can be up to 18 frames in parallel in this switch, in this network. So we see that with the same cabling system, by going from hubs to switches, we can increase potentially in this small network by a factor of 18 the throughput of the network. This is why we use switches today. And the reason the switches and the bridges are the way they are with this clumsy spanning tree and all the like is because we've kept the requirement to be transparent. So the MAC layer is the same whether we have all those devices or not. And in particular, for IP, everything that has a MAC layer is the same whether it's Wi-Fi or Ethernet. Let's talk in details of the Ethernet packet size. Packet format, which you can observe with Wireshark, TCP dump, or similar programs. This is showing the bits as they are transmitted along the wire, starting from the top. So when an Ethernet packet is transmitted, we start by the top. One particularity of the Ethernet physical layer is that it is asynchronous. Synchronous usually means anything, so this word is practically void of any concrete meaning. In a physical system, Synchronous means something has to do with the clock. When the physical layer sends something over the wires, it sends a waveform, an analog system. Then the receiver receives this analog system and has to decode it. In order to decode it, you need to sample. You sample with a given clock. Now, with which clock do you sample? That's a synchronization problem. Normally, every device has a clock, has a quartz, and then the sender has a clock, the receiver has a clock. The two quartz are never exactly the same. If you have a watch, you see that even a very accurate watch, after one day, it is 1 second off, perhaps. Right? So very good clocks are of approximately accurate, an approximate accuracy of 10 to the minus 6. After 10 to the power 6 bits, you're off by 1. Now 10 to the power 6 for bits is not so much. So you have a problem in physical layer in that if the receiver and the sender clock are, as they are by physics, not exactly the same, then you have mismatches. If you start sampling a signal, after sampling 1 million times, you're off by 1, then you read the wrong bits. So you have a problem. There's millions of ways to solve that, or there are two ways essentially to solve this. There's a simple and a complex way. The complex way is to synchronize everything. So you put an atomic clock somewhere and you build a monstrous complexity to synchronize all the clocks of all the machines up to, with GPS for example, up to a few tens of nanoseconds of accuracy. That's what we do in the smart grid, for example, when we measure the phase angle of electrical quantities. We don't do that in Ethernet adapters. Instead, in Ethernet adapters, we use the other way of doing it, which is we don't synchronize the clocks, but instead we use very short periods where we need to be relatively accurate. And so every Ethernet packet is separated from the next Ethernet packet by a short period of silence. And there are special hardware devices called phase lock loops that are able to analyze, for example, a sinusoid and find where the peaks of a sinusoid are. And by doing that, you can have an accurate clock, not accurate, an approximate clock that will help you to read the signal. But this requires some training, and this is why in Ethernet packets you have what is called a preamble. It's a number of bits that are not part of the Ethernet packet itself. When you do a Wireshark stuff, you will not see the preamble. They're just here to train the phase lock loop to get the clock right, to get the offset of the clock right. Once you get the offset of the clock right, you read the packet, and for the next packet you will reset your clock again on the preamble. This is how Ethernet works. We say it's asynchronous in the sense it acquires synchronism only for the lifetime of a packet. For every other packet, it forgets about synchronicity. Which is perfectly fine because we're transmitting packets. So we don't need to be synchronized other than for decoding the signal. Telecom networks that try to transmit bits end-to-end, not just packets, have to be synchronized. But this is technology of the past. Today, everything is packetized. So the Ethernet way is the correct way of doing things. In practice, when you send a preamble, you need to say when does the preamble end and when the packet starts. So you have a special marker called the starter frame delimiter, a special sequence of zeros and ones that you are looking for in the packet. When you see that, you say, now the packet starts. Everything you can read when you do Wireshark is a thing in color. You get only this here. So the true Ethernet packet for us contains all those fields. DASA are destination MAC address and source MAC address, 48 bits each. A type that says what is the higher layer contained in the payload. Here, the type is for us typically IPv4 or IPv6. As we have seen, IPv6 is not a different type of IP, but is truly a different protocol. So it's seen here in the Ethernet packet. ARP, used for IPv4, as we have discussed last week, is also a special type of its kind, but this is historical. if we would redo IPv4 today, which we would not, we would do IPv6 directly, but if we would redo IPv4 today, ARP would be a packet inside ICMP, which would be inside IPv4. But this is what we see on Wireshark. Then there is a long, long list of other types. EtherTalk, AppleTalk on Ethernet, lots of protocols of all kinds. Most of them has disappeared except in standards body. And in the telecom and smart grid world, you still find a large number of things, but they will more sooner or later disappear, except for one or two that are of interest. MPLS. MPLS is a special form of MAC layer that we'll discuss at the end of the course. That does what is called connection-oriented networking, and special hardware stuff, like if you want to carry clocking information, not for transmission, but because you truly want to synchronize a clock. For example, you're doing high precision measurements with a sensor that needs to have an accuracy of a fraction of a microsecond, then you need to carry special packets for the timing that cannot be just handled the usual way, because the usual way is to have a switch, which is a queuing system, so the waiting time in a queuing system is random, so you cannot have very accurate measurement. We synchronize the clocks, for example, of this machine using packets, using the NTP clock protocol, network time protocol, but the accuracy of it is compatible with the variable processing time in routers. So you have an accuracy of a fraction of a second, which is good enough. If the clock of my computer is accurate up to 1 second, I have an accurate clock for human beings. Now for machines, if you want microsecond clock, you need special treatment by the switches. They have to do special things, so we have a special type. Then you have the packet itself, which is, for example, an IPv4 packet. And then at the end, you have a code, which is called a frame check sequence, which is 32 bits, 4 bytes of a code, like some of you have seen in the information theory courses. It is a code that is able to detect bit errors and is able even to correct a single bit error. So it can detect bit errors in the entire Ethernet packet here. Most hardware devices require that. The code provides bit error detection, and we could ask, why is that? Well, because when people build computers, they want to have a complete digital systems that are free of errors. If you do voice over IP, you could say, well, I could live with a few errors, but all systems, practically all, except from digital voice using PCM, cannot live with errors. So today, in any TCP/IP stuff, assumes that the physical layer delivers packets that are free of bit errors. Now, this is true up to some probability. If I have 32 bits of code, I still have a residual probability that there is an error that is uncatched. And this probability is 1 out of the 10 to the power, 2 to the power 32. So 1, 10 to the minus 9 approximately. It is still possible that an error occurs. Now on wired systems, bit errors are very rare, of the order 10 to the minus 11, 10 to the minus 12. So the uncatched bit errors are 10 to the minus 9 times 10 to the minus 11, so it's fairly rare. Of course, when you're Facebook or Google, the amount of data you manipulate is so large that even those very small error probabilities multiplied by the 10 to the power 20 or 10 to the power 30 packets that you receive will make that once in a while there is an error. So on very large storage systems, you do find errors that are uncaught. We'll talk more about that a bit later. We've discussed the addresses. So this is the view, the intellectual view of the MAC layer. That is a truly shared medium. So the concept is I put a destination address, all systems receive it, and whoever is the destination copies it. We've seen that the bridges do something similar, but of course they process the address here. But remember, bridges are transparent, it's the same. is done exactly the same way. Except with a small difference, of course. Now, if you start Wireshark here at B, you will see the packet sent to the router. Whereas at the bridge, will you see it? Probably not. Probably not, except if the bridge, for some reason, doesn't know where the router is, which is very unlikely because there's a lot of traffic going here. So if the bridge doesn't know the destination MAC address, it might broadcast it. But this is, except for the airport example I mentioned before, it is very unlikely to happen in reality, so you will not see it. So bridges are slightly more secure in the sense they don't show everything to everyone, but they're not really secure, right? Everything is sent in the clear to everyone. Broadcast is also supported. We've seen that we use broadcast very often. As we know, the MAC address for broadcast is FF all ones. And the idea of broadcast was very natural in this environment. We can understand why, now we can understand why there's so much use of broadcasting in the local area network in LANs. It is because the mental model of a LAN is this. It is a truly broadcast medium. So broadcast is cheap, it's for free. Anything is sent to everyone anyhow on an old-styled Ethernet. So broadcast was a very natural thing to do. You just make the address that says everybody should copy. There was no additional cost in broadcast here. Now, if you have a network of bridges, that's another story. Of course, a broadcast frame is truly sent to everyone on all the links. But as we have seen, if we have bridges, they separate the collision domain. So all the links could do things in parallel. If you send a broadcast, you kill that. The same frame is sent to everyone. How do we do broadcast on the bridges? Well, that's very easy. The bridges need a tree to operate. If they have a tree, they can use the tree for broadcasting. They can send simply the packet to everyone. If the active topology is a tree, there's no TTL problem of any kind because you send it on something that is free of loops. We've discussed multicast a few times. We've seen, for example, the solicited node multicast address. Ethernet supports multicasts. So there are MAC addresses of a special type that are group addresses. They have a special bit, bit 8. When bit 8 is equal to 1, that means it's not the name of an adapter, it's not the serial number of an adapter, it's a logical identifier of a group at the MAC layer. So a group within a local area network environment. Ethernet adapters, in principle, except if you're doing Wireshark, does not receive the data that have destination MAC address equal to a group address, except if the operating system has actively decided to subscribe to receive, and this is called subscription. So like receiving TV or receiving a given channel. By the way, this is how Bluewind TV, Swisscom TV works. It uses IP and MAC layer multicast. So if, for example, B and C subscribe to this MAC multicast address, this is equivalent to saying the operating system instructs the Ethernet adapter to copy means receive, all the frames that have this destination MAC address. That's on the end station side. Now, what happens inside the network, if I have a true network and not just a cable like this, well, depends on the bridges. On the non-smart bridges, they simply broadcast because it's very hard to know who has subscribed, right? The thing should be plug and play. And there is, in the MAC layer, there is no subscription protocol. So it's impossible for a bridge to know whether an Ethernet adapter has been instructed to listen to a given destination multicast address. So in principle, it's impossible to do anything else than broadcast. However, as we will see in a number of other instances, it is possible to violate a bit the principle of layering because all of this is software and man-made systems. So anything except speed of light can be worked around. So what smart bridges do, they listen to the subscription protocols at the IP layer. Because at the IP layer, if this is your TV and you decide to tune to channel Swiss number 2, then your IP software in the IPTV box will subscribe, will send an IP message, an ICMP, called IGMP in that instance, message to the router saying, I would like to receive the things for that destination address. And the bridges will do something they should never do, but if they are smart, they do. They listen to that, so they try to catch all the IGMP, the subscription packets, and they see what's inside. And by reading this, they will see, oh, this guy is listening, therefore I will, in my in my forwarding table, I will send the packet there. Voilà, a quick recap. The protocol type in an Ethernet header, does it indicate that the data is a TCP packet or not, or an IPv4 packet, or both? Or none, perhaps? Five more seconds. That was an easy one. The answer is, of course, there is no indication at the Ethernet level whether it's TCP or not. And a normally constituted bridge doesn't care. We have something that works with IPv4, this network. Right? We add IPv6 to the network. So we had an old style network that works with IPv4 only, and then we upgrade all the software in all the workstations to IPv6. Do we need to change something in the bridges? Five more seconds. No, that's the correct answer, at least as a first approximation. If I have smart bridges that do the multicast stuff and they work only for IPv4, I might have a problem. But a priori, a non-smart bridge doesn't care. And that is probably one of the most important features of the MAC layer today, is that they're independent of the higher layer, except for the smart one for multicast. But they're independent of the higher layer. In particular, when we move to IPv6, there's nothing to do in the bridges. That's good news. At least one place where the transition to IPv6 is easy. Let's conclude with an additional complexification of all this, which is called the virtual local area network. It's almost impossible to understand why there are virtual local area networks, but nonetheless I'll try to explain. And again, it's all based on history. I mean, we see that today a bridge is essentially the same thing as a router, except it does its forwarding table differently. But because people depend so much on the way the networks are organized, today all corporate networks are based on bridges, switches, and then a higher layer that uses IP and routers. For example, at EPFL, if you're in my lab, you are also in the same local area network of my lab. Now, if you're in my lab, but for some reason your office is in the smart grid building, then you're in my lab as well, but you're in a different local area network, which means you have a different subnet prefix. And that happens all the times in companies. Here at EPFL, we change relatively at a slow pace, but in companies, you are reorganized every 2 years. So having the wiring system being one-to-one mapped to the subnet of IP is a nuisance, right? You would like, no, you can say who cares, after all, as long as I have an IP address, I can do everything. So that's the good answer, I think. But a number of companies care. So a lot of things are organized with access control. For example, you can access this server only if you are on this local area network. That's a fairly desperate attempt to bring security, but it's done quite a lot. Right? So the solution to this disparate attempt is called virtual LANs. You make the LANs virtual by decoupling from the physical wiring to the MAC layer. How is that done? So for example, I'll steal 2 minutes of your time to conclude on the next slide. Here I would like to have 3 virtual LANs, one for each color. And I would like to be able to support the facts that, for example, the red and the green are on the same switch. How is this done? Well, it is done by adding to the Ethernet header something that is called a VLAN tag, which is a number, a local area network number. And then the switches, they handle those numbers as separate local area networks. So when C sends a packet to D, for example, the switch has one forwarding table, one red forwarding table, one green and one blue. When it receives an Ethernet packet with a red label, VLAN tag, then it considers it's a red packet and it applies its red forwarding table. The switches also make one red spanning tree, one green spanning tree, one blue spanning tree, so they do one for each, and then it is as if things were completely separate. And I will conclude with the last clicker test to train you for tomorrow. Assume I'm using that stuff on a single switch to keep things simple. I have a red and a green virtual LANs. A has a packet to send to C. S1 is a switch that does this virtual LAN stuff. What will A do? I propose several solutions. Five seconds and you're free. Well, this time the majority is not right. None of the above. Well, the red and the green LANs are separate. So A and C are on different LANs. So when A sends a packet to C, what should A do? Well, should have, hopefully, an IP forwarding table that has the destination of a router. A should send to a router. Remember, virtual LANs are like physical LANs. They are separated. You don't communicate from LAN A to from LAN B without a router. That's IP principle, one of the 2 IP principles. So the truth is there must be a router somewhere, like this guy, and what A will do is find the MAC address of the router. A doesn't need to know the virtual LAN tag of the router because the virtual LAN tag is put by the hardware and is completely transparent to the software because everything stays within the same LAN.